Hello everyone, my name is Sentinel-1. I'm a Google Earth Engine expert. Today I'm going to show you how to do flood detection in the Google Earth Engine platform by the Sentinel-1 images. It's very helpful tutorial enabling you to find flooded region and calculate the floody area actually. So for the first step, we need to identify the location of the interest or the region of the interest. The region of the interest should be a region that's already flood occurred. Unfortunately, in 2019, we had a severe flood event in Iran, specifically in the north and west of country. So accordingly, I want to select the part of north of country that was under the heavy flood condition, and then by the drawing tools here, first I identify the study area location by the rectangle tools. And then to have a focus on my study area when the code is run, I use map center object to have focus on the location of the interest by the geometry that is the name of the rectangle we already draw it here. So then we need to call those of Sentinel images available before and after the flood events. So accordingly, I make a variable and we entitled as before equals to through the search places and data set. We need to call Sentinel-1 images. Sentinel-1. Here you can see that synthetic aperture radar GRD available from 2014, imported into the code as an image collection. Then we have an image collection for before variable. So next we need to set filter date and filter bound that are typical filters that is used for all of the satellite data in the Earth Engine platform to narrow down image collection into a specific period and into a specific location. The filter date equals to time start and time end. So here I make a new variable, time start and time end. Unfortunately, the flood event occurred in the 2019, so we need to set the time start to 2019 and time end to 2020, just like that. And then by that filter bound, so we need to limit those of image collection into our location by the geometry or drawing or the region we already drawn. So then in the next step, we need to set some filters that are specifically used for Sentinel-1 images. For example, filter date and filter bounds are typical filters. For example, time start and time end, and bounding satellite data into a specific region. It is already, all of them are typical for all of the satellite data available in the Google Earth Engine. But for the radar images, we need to do some filtering process based on the Sentinel-1 properties. And these kind of properties maybe is not available for other satellite data in this platform and also in any other kind of platforms. So here we have a filter entitled as filter dot list contains. We need to call those of Sentinel-1 images that their property including transmitter, receiver, polarization equals to VV, vertical, referring to the kind of polarization in the radar images or the direction of the electromagnetic movements in the microwave region of electromagnetic spectrum. So then we have Earth Engine filter. Here we will have an equal filter for the instrument mode. The instrument mode should be equals to IW. IW means interferometric width. So then by the print function, you can see that how many images are available for 2019 in this region according to the filters defined. In the right hand, so we have a problem in writing. Before here, there is something wrong. And now you can see that over 170 elements are available for only 2019 and this region. Now, based on the flood event date that is occurred on March, we can filter our data to 1 month before or the month of the flood occurred. For example, here I make a calendar filter, Earth Engine that filter that calendar to the 1 month before the flood. The flood was in March, and now we want to have, for example, February as a before time or as a before month. So in this code, so calendar range start month will be February 2, and end month will be February or month number 2, and the unit here should be month again. If you run the code again, only 12 elements are available for this period, and all of them, you can see that all of them are related to the February, the second month of the year in 2019. So in the next step, you can see that for each element, 3 bands available. As you can see, there are 3 bands here, VV and VH, and also angle. The VV means that the electromagnetic radiation moving vertically from the satellite or from the sensor to the target vertically and receiving from target to the satellite or sensor vertically. VH meaning electromagnetic radiation moving vertically from the sensor to the target and coming back by horizontal shape and horizontal direction. So we need to use vertical or VV band because provided more energy or more electromagnetic radiation and with less noises. And according to this, I use .select VV to select only VV bands here. Then I make a minimum image by .min for the whole month. For the February 2019, I get a minimum value in each pixel. By map.add layer, we can visualize before event image actually. .clip based on location of the interest and leave the visualization characteristic empty, and also instead of the layer setting name here I type before, and then write false here provides actually prevents from automatic visualization or automatic uploading the result in the Earth Engine. So run the code again, and here we focus on the study area by the map.center object, and here you can see the before image for February 2019. Here by a visualization, by a stretching process, we can improve the contrast of final image, and here we will have a radar image for February 2019, the darker area showing the water surfaces, as you can see, compared to the satellite image, high resolution image in the base map. You can see that the water areas showing darker regions and also brighter regions showing different kind of phenomena such as agriculture, soil, and urban area. For example, the urban structure showing the higher backscatter values. It means that the microwave radiations highly sensitive to the roughness of the surface, and in the man-made structure the rate of backscatter strictly increased. And here you can see that the urban area has the higher backscatter value compared to the other phenomena and land covers. Here by different type of stretching you can improve the contrast of image, and also local residents near to the city, all of them colored by the light white region, and you can see them accurately. And these are residential areas with higher backscatter values, and also all of the actually water surfaces. You can see that all of them showing a dark and a smooth region. And when you zoom into the radar images, you can see some effects such as salt and pepper effect, which is a speckle effect. Actually, a speckle is a kind of visual characteristic of radar images after interaction between microwave spectrum microwave radiation and different phenomena on the surface. So to reduce the impact or effect of the speckle or the salt and pepper pattern in the image, we can use some low frequency filters in the Earth engine. So here, if you want to reduce the impact of the salt and pepper pattern in this image, we can define a function entitled as despeckle, because we want to reduce the impact of the speckle, and considering each input image as an img here, and then we return the input image after applying a low frequency filter. Here we have in Earth engine, for example, focal mean or focal median or focal mean. Both of them can be used to reduce the high frequencies impact coming from speckle noises in the radar image. For example, try with focal mean here. The focal mean, we need to set a radius. The radius showing that the target of spatial resolution we need to have after focal mean applying actually. For example, I want to have information up to, for example, 30-meter spatial resolution. So here I set the radius as 30, and the kernel type should be a square. Why square? Because the satellite image, in the satellite data, pixel geometry including a square shape, or showing a square shape here. So it's a square, and then the units should be here meter, because we want to have 30-meter spatial resolution after applying low pass frequency filter or focal mean here. And then in order to have the property of input images, we need to set img and img.property names inside the copy properties. So before mean function, we can apply despeckle function on each available image here. So to do this, I add .map as a loop to apply despeckle, just like that, despeckle function on each data in February 2019. So save your code if you want and then run it. So here we have a problem. This should be meters, not meter. And then run the code. Go into study area, and here the before image is available. Improve the contrast by 90% stretch, and if you zoom in more, you can see that the image smoothed after filtering process, and it means the impact of a speckle filter a little decreased in the final images, because we don't need to the speckle filter, we don't need to the speckle impact in the radar images to find the flooded region. So back to the code, and then after learning about dealing with Sentinel-1 data in the Google Earth Engine platform, now we want to repeat the process for the March 2019, the month that the flood event occurred. So just copy the before variable and map.add layer and paste it again with the little changes. Instead of before, we will have after, same time start and time end, but we need to call this data for March. Instead of 2 or February, we will have March or month number 3. So the question here is why we use minimum function to calculate the minimum backscatter values over the timestamp actually, or over the time period, over 1 month. Why we use the minimum value? It's very simple, because in a radar image, as you can see, the water area or the lake or flood region, because of the water available in the region, we will have a lower backscatter value. And that's why when you get the minimum value per 1 month, finally you can show all of the water contents or all of the lakes and waters that are available in that month in your region. So as you can see here, for the after one and before one, we will get the minimum value. Then by the map.add layer, I can get after image, the minimum value for March, then clipped by the geometry, and its name in layer setting will be after. So save your code and then run it again. When you run the code, you will have 2 images, one before in the layer setting, one before in February, and one after, the after events curved. So here you can see the after flood, you will have more water in your study area. You can see that, for example, this region or this urban area, after flood, you can see that surrounded by the water. It's very, very dangerous situations for the people and residential and also residents who are living in this area. You can see that many areas covered by the water after the flood situation. So there is a clear difference between 1 month before and 1 month after because of the flood. And when you get the minimum value, you can show all of the waters available in your study area. So in the next step, after see the visual characteristic of flood condition or the flooded condition in your satellite data, you can get the differentiate or you can get the subtraction between after events and before events to highlight the flooded region more accurately. So back to your code, and then here make a new variable. Here we have a change meaning the difference between the after image and before image. So if we get the subtraction between after and before image, you can highlight the difference between these 2 dates, which is flooded region. So as you can see here, change calculated based on this relationship, and then by map.add layer you can show the change map. But before then, it's important to be clipped based on the location of the interest or geometry and leave the visual characteristic empty, and the name for the layer setting is flooded region. And then set automatic visualization as false. That prevents automatically open the layers after code running. So this is flooded region, but there is no good contrast here, and we can't identify anything or detect flooded region accurately. To make it better for the visualization and interpretation, you must increase the enhancement by 90% through the layer setting. But there is something wrong because we wanted to highlight the flooded region. To do this, it would be better to get the difference between before and after image because we want to highlight the flooded region. It means showing flooded regions with a brighter color or white area, and this queen, and also we want to separate the flooded region by the brighter color from the other regions in the results. So then I change the code and we will have a new flooded region image. Again, the same problem, low contrast, and by the 90% increase and apply, you can see that the flooded region highlighted. After we change or we replace the after and before in the change equation, you can see that the flooded region highlighted very well. And now we can, by setting a threshold, we can make a mask based on the threshold to separate the flooded area for the further calculations such as flooded area calculation and so on. So now in this next step, histogram will helping us to see that how the range of values changing in the change image or in the flooded image. So by the print function, we can visualize the histogram, user interface, chart, and histogram. In the histogram, the first argument is the target image change, and the region is the geometry, and then the scale will be 30 because already the spatial resolution reduced to the 30 meters by the focal mean function here. So save your code and run it again. In the right side of this in the right side or in the right panel, you can see we have a problem for the reduced region. It meaning that too many pixels in this region for the 30-meter spatial resolutions. When you are working with the highest spatial resolution data for the environmental studies such as Landsat and Sentinel, higher spatial resolution causes some sort of problem in computations because of too many pixels in your study area and returning such kind of errors. To solve this, you should reduce the spatial resolution number or reduce the number of scale. You must increase the value of the scale in your histogram. For example, now I change it to 100, and finally you can see the histogram of vertical band that is calculated based on the difference between February and March. So here we will have a single mode histogram, and here as you are watching the flooded region with the brighter color, let me show you again. When you are watching the flooded region or flooded area with the brighter color, it means that the higher values showing the flooded region and lower values showing non-flooded region. So by inspector, you can check in the image what is the range of flooded region. For example, if I click here, you can see that the before event -12 is the value of backscattering for this region, and after it is covered by the water in March, you can see that reduced to now -26, meaning that covered by the water and the scattered and also the radar backscattering reduced a lot. And finally, in the final image, we will have a positive 13. That's meaning that here already covered by the water in the flooded situation, and now we can set some numbers such as 13 or above to select the flooded area. So, for example, we can check it in the histogram that is already calculated. For example, here the range of the values ranges from -37 to the +30, for example. And as we are watching the flooded area with a brighter color, meaning that definitely we need to find the threshold among the positive values here. And as the flooded region showing a small part of the image, meaning that the number of the pixels with these values not too much. And here you can see that high frequency numbers definitely don't show the flooded region. So we need to find the desired threshold in the values or in the ranges that have provided lower frequencies. For example, maybe the values greater than 6.5 could be a good threshold to make a distinguish between flooded region and non-flood region, actually non-flooded regions. So we can try it. How we can do this? By the map.add layer and setting a threshold. For example, here I have a change map, and then I set a threshold to make a binary image based on the values greater than 6.5. We need to have number 1 for the values above 6.5 and number 0 for those of values below this threshold. So then clip it based on the geometry, visualization empty, and the number is flood threshold or flood THR, and then we will have false at the end. Run the code again, zoom in into your location, and then open it. So as you can see, the flooded region or the flooded region showing with number 1, and all of the non-flooded region showing by number 0. So meaning that maybe we set a good threshold to make a differentiate between the flooded region and other regions. You can compare them visually by 90% stretch. This is the change map, and this is a threshold that we set. I think it works good. Yes. And also there are some noises, or there are some small pixels, and that you can remove the small pixels by increasing the value of threshold. For example, if we set value number 7 instead of 6.5, lots of these points and lots of these errors will be removed. This is the new threshold image. You can see that lots of the noise is removed, and also I think it's enough for this step. And then in the next step we can calculate the area of flooded region by the further functions in the Google Earth Engine platform. To get an area, we make a flood threshold here. So here we have a change map to select those of values, those of pixels greater than number 7 as number 1, and set the value 0 to all of the pixels, all other pixels. And then we need to have a flood mask equals to get flood threshold dot update mask based on flood threshold, flood THR. Actually, this expression or this function update mask helping us to turn the 0 values in the binary image into the NaN, and also we can filter them in the further processing, because we only want to work on pixels with number 1 in the next step. So then we want to get the area of flooded regions that is already identified by number 1 in the flood mask. So to do this, we will have flood area equals to get flood mask dot multiply used to apply a function that here is the pixel area. In order to convert the unit of measurement or unit of calculation from the square meter to a square kilometer, we can divide the values into two square kilometers by 1 million. So, and then for each pixels that's already highlighted by number 1, we have the area based on the pixel area function that is already used for our calculation. Now we want to get sum of the area of the flood region in the next step. So then finally the flood area in the region, not in the pixel, equals to get flood area dot reduce region. Different arguments here. For example, the reducer will be Earth engine dot reducer dot sum to get the sum of the area of pixels, and then instead of geometry we will have a geometry or location of the interest, and a scale is also important. The scale should be 100 to avoid from such kind of errors that we already faced about too many pixels in this region or something like that. And also in order to convert the flood area region to a value, and to the values we use dot values and dot get the first values here. So finally, to show the value, we can use print that region, but we need to show it by Earth engine dot number to show it as a number here. And finally, we will have the area of flooded region equals to based on a square kilometer. If you run the code, in the right side we will have the area of flooded region, which is 340 square kilometer based on the region of the interest or the location that we already selected by the drawing tools. I hope this tutorial can help you to do flood detection for your desired location. If you had any problem or any question regarding this code, you can put your comments in my YouTube page or or page of this tutorial, and feel free to contact if you had further question or help.